ultimately regulates the total amount of carbon dioxide in our atmosphere.
With carbon dioxide levels around the world rising, how much CO2 can rainforests like this one absorb? And how important is their role in protecting us from further global warming? Enquist and a team of U.S. scientists think that fractal geometry may help answer these questions.
Baseline. Let's try to get the height of the tree measured here.
They are going to start by doing just about the last thing you'd think a scientist would do here. Cut down a balsa tree. It's dying anyway, and they have the permission of the authorities.
So Christine, as soon as you know the height of that tree, we can actually figure out the approximate angle that we need to take it down on.
Hooking a guideline on a high branch helps ensure the tree will land where they want it to.
Very good, very nice. Jose, perfecto.
Enquist and his colleagues then measure the width and length of the branches to quantify the tree's fractal structure.
8.
10.06.
No, that's 8.
6.3.
0.03. 608. 7 on the nose.
They also measure how much carbon a single leaf contains, which should allow them to figure out what the whole tree can absorb.
So if we know the amount of carbon dioxide that one leaf is able to take in, then hopefully using the fractal branching rule, we can know how much carbon dioxide the entire tree is taking in.
Their next step is to move from the tree to the whole forest.
All right, this is good.
13.2, 3.3 R.
We're going to census this forest. We're going to be measuring the diameter at the base of the trees, ranging all the way from the largest trees down to the smallest trees.
3 meters above the ground.
And in that way, we can then sample the distribution of sizes within the forest.
It's 61.8 centimeters.
Even though the forest may appear random and chaotic, the team believes it actually has a structure. One that, amazingly, is almost identical to the fractal structure of the tree they have just cut down.
The beautiful thing is that the distribution of the sizes of individual trees in the forest appears to exactly match the distribution of the sizes of individual branches within a single tree.
If they're correct, studying a single tree will make it easier to predict how much carbon dioxide an entire forest can absorb. When they finish here, they take their measurements back to base camp, where they'll see if their ideas hold up.
So is this is the tree plot, right?
Yeah. The cool thing is that if you look at the tree, you see the same pattern amongst the branches as we see amongst the trunks of the forest.
Very nice.
Just as they'd predicted, the relative number of big and small trees closely matches the relative number of big and small branches.
It's actually phenomenal that it is parallel. Yeah. The slope of that line for the tree appears to be the same for the forest as well.
So I guess it was worth cutting up the tree.
It was definitely worth cutting up the tree.
So far, the measurements from the field appear to support the scientists' theory that a single tree can help scientists assess how much this rainforest is helping to slow down global warming.
By analyzing the fractal patterns within the forest, that then enables us to do something that we haven't really been able to do before. Have then a mathematical basis to predict how the forest as a whole takes in carbon dioxide. And ultimately, that's important for understanding what may happen with global climate change.
For generations, scientists believed that the wildness of nature could not be defined by mathematics. But fractal geometry is leading to a whole new understanding, revealing an underlying order governed by simple mathematical rules.
What I thought of in my hikes through forest, that, you know, just a bunch of trees of different sizes, big ones here, small ones there, looking like it's sort of some arbitrary, chaotic mess, actually has an extraordinary structure.
A structure that can be mapped out and measured using fractal geometry.
What's absolutely amazing is that you can translate what you see in the natural world in the language of mathematics. And I can't think of anything more beautiful than that.
Math is our one and only strategy for understanding the complexity of nature. Now, fractal geometry has given us a much larger vocabulary. And with larger vocabulary, we can read more of the book of nature.